Hello everybody, welcome to this channel. I'm Payman Hassari. In this tutorial, I'm going to teach you how to build a multi-class classification using neural network in RapidMiner. The dataset that we use is called Fashion MNIST that can be found easily on internet. It contains 60,000 examples, and each example is a 28 by 28 grayscale image associated with label from 10 different classes. Each image it has 28 pixel in height and 28 pixel in width for a total of 784 pixel in total. Each pixel has a single pixel value associated with, indicating the lightness or darkness of that pixel, with higher numbers meaning darker. This pixel value is an integer between 0 and 255. The classes are 0 for t-shirt top, 1 for trouser, 2 for pullover, and all the way down to 9 for ankle boots. Let's take a look at the data. I bring the dataset into the process panel and connect it to the output and run the process. I have 60,000 example with 785 attributes. The first column is our target variable, and the rest are the attributes. And as you can see, the data are integers between 0 and 255. We can take a look at the statistic as well. And we see here that the label is integer and it's a number between 0 and 255. The rest are also integer, and as we can see, there is no missing value here. I can take a look at the distribution of the label as well by opening up the visualization, and I want to take a look at the bar plot. And this is the distribution of each class in the target variable. And as you can see, the data type of the label is integer. Because we're going to build a classification problem, we need to change the data type from integer to category. And in order to do that, we use an operator called numerical to polynomial. Let's bring the numerical to polynomial operator to the process panel. Connect these two operators together and configure the operator. The attribute filter type is single and the attribute name is label. The advantage of working with image data is that there is not much to do in terms of preprocessing. The only step that we do is to standardize the data. And in order to standardize the data, we use an operator called normalize. Bring the normalize operator into the process panel, connect these two together, and configure the operator. And because the data is a number between 0 and 255, I'm going to configure the attribute filter type for all features that I have. And the method that I'm going to choose, I use the range transformation. By range transformation, I transform each data from 0 to 255 into a range between 0 and 1. Next is to specify the target variable and split the data. In order to specify the target variable, I use an operator called setRole. Bring the operator into the process panel, connect it to this operator, and configure it. The attribute name is label. And the target role, there are different options, but we have to choose label because label is the one that tells RapidMiner where this label is our target variable. Next, I bring split data in order to split the data into training set and test set. I configure this operator, and for the partition, I use the edit enumeration and I add entry. The first entry is the proportion of the data for the training set. I use 80%, 0.8, and I add another entry, and the rest, which is 20%, is for the test data. Hit OK, and I need to choose the sampling type. There are different methods that I can choose: linear sampling, shuffle sampling, stratified sampling, or automatic. I'm going to choose automatic, and in order to reproduce the same data, I choose the local random seed to be equal 1. Now that the data is ready, I'm going to build a neural network classifier. In order to do that, I call an operator called deep learning, bring the operator here, connect it to the split data, and configure this one. The first parameter is activation function. There are different options to choose for activation function, like 10H, 10H with dropout, rectifier, and so on. I choose rectifier. The next one is number of hidden layers and the number of units for each hidden layer. By default, there are 2 hidden layers. We can choose any number for each one of them, like 32 for the first one. And for the second one, you can pick any other number or you can remove it. And I'm going to remove that one and hit OK. And we have epochs and other parameters that we can configure, but I'm going to leave them as default. Now that our model is built, I need to calculate the performance of the model. In order to do that, I need an operator called apply model. Bring the apply model here. Connect the model to the model and output to the unlabeled data. And apply model has no parameter to configure. Next is to call performance for classification. Bring the operator here and connect it to the apply model and configure this one. The main criterion, I'm going to choose the first one as accuracy, and that is the metric that I'm going to measure for this problem. But there are other parameters and metrics that we can choose, like weighted mean recall, weighted mean precision, and relative error, and so on. And that is the way I configure the performance for classification of the model that we built. Next, I connect it to the output and run the process. The deep learning model is being built. And here is the performance of the model, where we have 98% accuracy on the training set, and this is the confusion matrix. We calculate the performance of the model on the training set. We need to calculate the performance of the model on the test set as well. In order to do that, I make a copy of the deep learning model using multiply operator. Multiply operator has no configuration. And in order to calculate the performance of the model on the test data, I use the apply model and test performance operator the same way we used it for training set, but the data for the apply model in the test case, we get the data from the split operator. And the rest is exactly the same as what we did for the training data. We can run the model now and see the result. The performance on the training set, we get 98% accuracy, and the performance on the test data, we get 95.41% accuracy.